Hello. This will be a demonstration of proposition 15 from book 8 of Euclid's Elements, which says that if a cube number measures a cube number, its side will measure its side. But if, on the other hand, conversely, we're given that the side measures the side, then we want to prove that the cube number measures the cube number. This is very similar to the previous proposition 8.14, but instead of dealing with square numbers, we're dealing with cube numbers. Also, like the previous proposition, you'll notice that there are two different givens, which means that there will be two different things that we have to prove, and thus two different cases or scenarios, as it were, that we'll have to deal with as they come to us. But beyond those two cases, there is something that remains constant between them, and that is the numbers a, b, c, and d. The two numbers a and b will be cube numbers, and their sides will be c and d respectively. So that c cubed is equal to a, and d cubed is equal to b. But what varies between the two cases is this part of the given. We are either given that the number a measures the number b, or we are given that the number c measures the number d. If first we're given that the number a measures the number b, we want to prove that the side c measures the side d. But if, on the other hand, we're given that the side c measures the side d, what we want to prove is that the number a measures the number b. Before even dealing with either of those two cases, we're going to construct several numbers. We're going to begin by making c squared. We're going to call that e. So c times c makes e. C times d, we'll take the product of c and d, call that f. So c times d makes f. And next, we're going to take the square on d, call that g. So d times d makes g. Next, we're going to take the product of d and e, call that h. So d times e makes h. And we're also going to take the product of d and f. This will be the number k. So d times f makes k. I will note one thing real quickly about the number h. You can either say that it is the product of d and e, or you can say it is the product of c and f, because either way, you end up with c times, either way, you end up with c times d. So if you say that it's c times f or d times e, it really doesn't matter, they'll be the same number. Now let's deal with that first case. If the number a measures the number b, we want to prove that the number c measures the number d. First, we'll note that our four numbers a, h, k, and b form a continued proportion. We know this by several uses of proposition 7.17, not unlike the previous proposition 8.2 and the more recent one 8.12. So if this sort of logic is a little fuzzy, a little confusing right now, it certainly was to me the first time I got to refer back to those previous propositions or my videos on them. Euclid doesn't rehash the logic here, so I haven't. The point is that the four numbers a, h, k, and b form a continued proportion so that a is to h just as h is to k, just as k is to b. We also know, or we were given, that the number a measures the number b. So what we have here is a continued proportion where the first number measures the last number, which then means by proposition 8.7, the first number also measures the second. So that because a, h, k, and b form a continued proportion, the first number a measures the last number b. The first number a also measures the second number h. Next, we'll notice that the number e has been multiplied by two numbers c and d to make two products a and h. E times c makes a because a is c cubed, e is c squared. So doing e times c is c times c squared, or c times c times c, or c cubed. That obviously makes the number a. And the number e times the number d, as we had explained in the first step, makes the number h. Which then means, by proposition 7.17, these two numbers which are multiplied, c and d, have the same ratio as the products a and h, so that c is to d just as a is to h. But you'll remember in the previous step we had just proved that a measures h, which then means by the definition of proportionality, definition 7.20, Because the number A measures the number H, the number C also measures the number D. And this is what we set out to prove, which means we're done with this first case of the proposition. But what if the number C measures the number D? We were given that. Well, we want to prove that the number A measures the number B. We go about this in quite a similar manner to the previous proposition 8.14. We begin by noting, again, that the number E has been multiplied by C and D to make A and H. Therefore, by proposition 7.17, C is to D just as A is to H. And because C measures D, we can then say by the definition of proportionality, definition 7.20, that because C measures D, A has to measure H. We're again going to remark that the four numbers A, H, K, and B form a continued proportion, so that A is to H just as H is to K just as K is to B. Again, this follows similar logic to propositions 8.2 and 8.12, so refer to those if you don't remember how exactly this works out. The point is that these four numbers A, H, K, and B form a continued proportion, and because we've just proven that the number A measures the number H, we can then say by the definition of proportionality as well that the number H has to measure the number K and the number K has to measure the number B, which means we have this continual series of measurements. A measures H, H measures K, K measures B. Therefore, by a property of numbers, A has to measure B. So it'd be sort of like 3 measures 6, 6 measures 12, 12 measures 24, therefore 3 measures 24. We see that this is a valid conclusion to draw. That because A measures H measures K, and K measures B, we can then conclude that A measures B, and this is what we set out to prove, which means we're done with the proposition. We've successfully handled both cases, therefore it's set our Q, E, D. You know me, I always like to give particular numbers to work with here, so let's do that right here. The cube number 8 measures the cube number 64, which then means that the side of 8 measures the side of 64. That means is that the side of the cube 8 is 2, and the side of the cube 64 is 4. And 2 measures 4. We can verify that this proposition holds. And we can do this in the converse. 2 measures 4. Therefore, the cube on 2 measures the cube on 4. The cube on 2 is 8. The cube on 4 is 64. So we see that this proposition holds. Now again, just like the last video where I briefly explained why exactly square numbers are called square numbers, I'm going to here briefly explain why cube numbers are called cube numbers. It's very similar though. There is a geometric intuition behind the naming of cube numbers. Say we have a line, say it's 4 long. Now we're going to build the cube on this line. That's fairly easy. Give me some time to draw that out. Hopefully it doesn't, look terrible. I'm a little bad at drawing things in 3 dimensions, which, of course, will come in handy in the next few books. But here we have the cube with side length 4. Now, what exactly is the volume of this cube? Well, it's going to be 4 times 4 times 4. 4 times 4 times 4 makes 64. So the volume of a cube with side length 4 is 64. And this is why we call cube numbers cubes. Because if we build cubes with side lengths of a given number, the area of that cube will be the cube or the thrice product of our given number. And that 4 times 4 times 4 makes 64. And this works in reverse. This explains why we call the cube root, is what we would say nowadays, of a cube number, the side. Because if we have a cube with volume 64, its side, or its cube root, as it were, has to be 4. So this is where the language of cube number and side comes from in this context. Now again, you might be able to conclude why exactly Euclid calls plane numbers planes, products of 2 numbers, plane numbers, and why he calls products of 3 numbers solid numbers. But I'll leave that until we get to those. That being said, this is all I have to say about this proposition, so I'll end the video here and move on to proposition 8.16.